Hello everyone, happy election day and welcome to this video on volume for rotations around an axis. So first off, let's go ahead and talk about graphically what's going on. So here's the situation I have. I was looking at this and I had an area, and yesterday we talked about how to find that area, but the thing that really came to mind is what if I took that area and I rotated it in a circle around the x-axis? So if I made a three-dimensional shape, so instead of taking an area, I made a three-dimensional shape by rotating it around the axis, how could I find the volume that's created? So if I take this shape and I rotate it in a line around the x-axis, that's here, the y-axis here, this is like coming out of the paper, what would be the volume of that three-dimensional shape? And that's what we're going to try and find today. So what we're doing today, we're doing what are called solids of revolution. And what a solid of revolution is it's what you get when you rotate an area or evolve an area around a line. And for now, we're just going to be looking at horizontal lines and vertical lines and not worried about diagonal lines because the math gets pretty messy. So we're going to be finding a three-dimensional volume. So let's look at an example here. So let's suppose we have the area between y equals root x, the x-axis, and x equals 4. And let's suppose this area is rotated around the x-axis, and we're going to try to find the volume. Now, the first thing you want to do, right, is try and visualize, like, what is the shape we're trying to find? So when you're doing these kind of problems, that's going to be my first step, is to draw a picture and then visualize. So the area that we're dealing with, okay, so let's see. We have y equals square root of x, so that's this curve. We have the x-axis, we have x equals 4. So what this looks like is it's saying, like, take this area right here that I'm going to highlight right now, and take that area and then rotate it around the x-axis. So we're going to rotate it around in a circle like that. Okay, so it's going to kind of make a three-dimensional shape, and that's what we're trying to find. Okay, so once we've done that, that's your drawing a picture, that's your visualizing. Okay, the next thing we need to do is find the bounds. So if we have two curves, we need to find intersections, but otherwise we'll just go ahead and just look at the bounds. Like in this case, obviously we're just going from x equals 0 to x equals 4. Like this is a pretty straightforward one. We're going there to there. Okay, so that's that. Now the third thing we're going to do, and I'm going to give you several key equations today, and I'm going to box all of them. And I'm going to find the volume. And volume is always going to be the integral of cross sections. And this is probably like the key equation from this chapter. Volume is the integral of cross sections. Put a big box around that. That's one of the keys. I'm going to put a big box around all the key equations today. What a cross section is it's like if you take a shape and you were to cut it in half, what would the shape be? So if I were to take my hydro flask and I were just to cut it right here, just cut it right through and then open it up into two, we would have a circle, right? There'd be a circle on the inside. And that circle is what's called a cross section. So if I wanted to find the volume of my hydro flask, what I would do is I would find the area of a circle and then integrate to add together all the circles along the length. And that's what you're going to do. You're going to find the volume of like one of these cross sections and then just add them all up, and that'll help you find the volume is by adding all the circles together. So that's what we're going to be attempting to do in this. Okay, so what we're doing here, going back to this picture, is we're trying to find a bunch of circles like this. So here's the circle at x equals 0. And as the x value changes, we see we get different values of this, different values. We get different areas of this circle, and then we add those together across all the x values from one side to the other. I know this isn't a square root equation, but it's the same general principle that I'm going to add these all together along my intervals. Okay, so if I'm going around the x-axis, I'm going in a circle, right? And hopefully you can see that, right? Those were circles. I was adding together all the circles. So if I'm going around the x-axis, I'm integrating a bunch of circles. Okay, so we should think, what is the area of a circle? Well, a circle is pi r squared. That's the area. And what is the radius? Well, hopefully we can see looking at this picture that radius is the distance out to the function. that radius is just the height of the function, that f of x. So if I'm going around the x-axis, my volume is going to be the integral of pi times that function squared. Okay, and that's the key equation that we're going to use to help us find an area around the x-axis. So I take the radius of the circle, the height of the function, and I'm just going to add all those circles up here from 0 to 4. And I'm just going to integrate and go across that region and add all of those together. Okay, so in this case, my volume will be pi times, I just put the pi in front, usually because I'm lazy. Okay, we're going from 0 to 4, that's what we found out in the second step, of the function squared, so root x squared. Okay, and in this case, we have pi times integral 0 to 4. Root x squared is just x, which is kind of nice, so that goes pi x squared over 2, going from 0 to 4. So when I plug in the 4, I'm going to get 4 squared root of 2, so I get pi times 8 minus 0, so I get a volume of 8 pi. So that's the general procedure for these problems, right? We find the cross-section, that area of the circle, and then I just integrate those circles across my region, right? I start at 0, I go up to 4. Okay, so that's how you do these problems. The next type of problem we're going to take a look at involves two functions. So let's say we take the area between y equals, well, I'll just draw a picture. So let's say we have the area. Here's my curve. So I'm going to draw, here's the curve, y equals x squared plus 1. And then I'm going to also draw the curve in a different color at y equals 5. Okay, so my area I'm looking for is this area in here that I'm trying to visualize. And I'm going to find the volume when this area is rotated around the x-axis. Okay, so what I'm doing here is I'm taking this pink area and I'm rotating around the x-axis. So the blue line is going to give me a radius in a circle, and the inner one's going to give me a radius in a circle. Interesting. So let's go back to the visual and see if we can get a sense of what that'll look like. Okay, so I'm just going to go ahead and add in another function here. So let's say now we have a second function. So again, if we take a look at what's going on here, we have just two functions. We have like a top from this parabola thing, and then we have a line. And if I rotate them around, okay, so that's what it looks like. So we have that hollow inside you can kind of see. And as I finish rotating around, that's the shape that it's going to look like. As for the cross sections I'm going to integrate, oh, those are just donuts. Okay, so as I add those together and go along, I just have a bunch of donuts here that I'm going to be integrating together. Okay, so what is the area of a donut? That's what we need to think. But that's the strategy. So as I integrate across this region, I'm just going to be adding all these donuts together from the left to the right. Okay, oops, wrong button. All right, so what I'm going to do, okay, first off, let's find the bounds. So I guess the bounds are the intersection points. So I need to set these equal to each other, and maybe you have to use your calculator in some cases. Here we just have x squared plus 1 equals 5, because those are my two functions. So that means x squared equals 4. So the bounds are x equals plus or minus 2. So when I want to find this volume, again, I'm going to integrate those donuts across from -2 to 2. So my volume is going to be the integral of these cross sections. And those cross sections, like we just said, are donuts. So what is the area of a donut? Well, if I have one circle inside of another circle, I can basically say, let's take the outer circle, which would be pi times some big radius squared, and let's subtract the inner circle. And that inner circle would still be a circle, so pi times little radius squared. So I can also think about pi times an r squared minus a little r squared, where this is again like my outer radius, and this is like my inner radius. So I can pull the pi in front. So that's what I'm going to do. So when I find this volume, I'm going to think about this as, or I'm integrating from -2 to 2 of pi times, okay, and my outer radius is x squared plus 1 squared. And when you think, oh, actually that's not the outer radius, geez. When you think about outer, you should think about the outer radius as being the one that's furthest from the axis. So outer is further from the axis. Okay, so what that's going to look like is, okay, so you can just like draw a little dashed line from your axis. Which one do you get to first? I'm rotating around the x-axis. So I get to the parabola first, so that's going to be my inner curve, and then I get to the line last, so that's going to be my outer curve. So the outer curve is the blue line, y equals 5. So what I'm doing is I'm integrating the 5 squared, because that's further away from the axis, and my inner radius came from the parabola. Now, if you want a handy formula for this that you would do, it's pi times integral of my outer radius, which would be f of x squared, minus my inner radius, which would be g of x squared. And this would be my key formula for, again, if I'm rotating around the x-axis. Okay, now we're ready to go ahead and plug this in, and this is an integral you should just do on your calculator, of course, right? This integral is disgusting. So now you can watch me type in buttons on my calculator. Great. So I just put the pi in front so I don't forget to multiply it. So I just do pi times, and then I'll do the integral of, okay, so parentheses, so I have 5 squared, and then I'm subtracting x squared plus 1 squared, and I'm integrating x going from -2 to 2. So if I remember to multiply by the pi, the answer I got was 227.870. Okay, so that's how we do it if we're rotating one curve or two curves around the x-axis. The other thing you might want to know is what if we're going around the y-axis, right? You guys love those problems. So if we have a volume around the y-axis, as you would imagine, these problems are almost identical. So if you have one function, the math is the same, it's just in terms of y, right? So you're just going a to b of pi times your function squared. If you have the area between two functions that's rotated around, that volume equation would be pi times integral a to b of f of y minus, oh geez, not minus, sorry, f of y squared minus g of y squared dy. So if you're going around the y-axis, your integrals need to be in terms of y. And we'll do an example of this in just a sec, but here are my two key equations for this. And this type of problem is really just plugging in these equations, figuring out which one's the outer and the inner. So let me do one example that looks like that. Let's say we have this example here where we have, all right, so we have the area between y equals x cubed and x equals 2. And that area is rotated around the y-axis. Okay, so if we're rotated around the y-axis, it's like saying, okay, so x equals 2, that's a vertical line, right? That's x equals 2. And then the y equals x cubed, we know what that's going to look like. Okay, so it looks like that. And the area that we're going to talk about is this area right here. Okay. Okay, now, by the way, this intersection point here is at 8, right? If you plug in 2, you get 2 cubes equal to 8. So that'll be one of our bounds. So if this is the curve of y equals x cubed, if I'm going to put this in terms of y, I need to convert this to x equals. So I'm going to do x equals the cube root of y. Okay, so great. Let's go ahead and do this. So my volume, again, if I'm rotating this in a circle, I'm going to get the donuts. So I'm going to get the outer radius coming from the line, the inner radius coming from the x cubed. And I'm just going to add all those donuts up from 0 to 8. So I'm going to start at the bottom and work up to the top. Now, the visual is the same. You're still just integrating donuts. You're still adding them from the bottom to the top. So because I'm going sideways, my bounds again are the bottom to the top instead of left to right. So my bounds are going to go from y equals 0 to y equals 8. And I'm going to do pi times, okay, and I'll have my outer radius squared, and I'll have my inner radius squared. And again, these equations are in terms of y, so they need to be x equals equations instead of y equals equations because I'm going sideways. Okay, so which one's my outer? Which one's further from the axis? Well, if we look at this picture and kind of draw a little line here, we can see the inner radius is going from the y equals x cubed, or the cube root of y. So that's my inner radius. That's cube root of y squared. My outer radius is the one that's furthest away. And that's always the same. That outer radius, when I get to the edge of my donut, is going from the x equals 2. So that's just the x equals 2 that gets squared. And then you plug this in your calculator or whatever and get a number. The key is the setup, right? This is the important part. Getting here, thinking about the outer curve and the inner curve. What are my bounds? Going from the bottom 0 to the top 8. And then just plug that in your calculator, right? So you're going to use your calculator for almost all of these integrals. Okay, So that's volumes around an axis, both in terms of x and terms of y. Thanks for watching, and I'll see you guys soon.